Hey everybody, we are going to enter the world of image pre-processing, and these are basically steps that we would take to get the imagery in whatever shape it needs to be so that we can do our ultimate analyses. And usually this falls into different types of image corrections. There's radiometric corrections, sometimes there's data compression or data reduction steps, and then geometric corrections. So this week we'll work on the radiometric corrections. We've done two of the potential pre-processing steps already. When we downloaded our imagery from the USGS, we conducted a radiometric calibration, which was essentially taking those raw digital numbers from the sensor and converting them, in our case, to reflectance. So that was one step. That essentially gave us at sensor reflectance. It was correcting for the sun angle and the date and the distance of the sensor above the surface and all of that. But it still wasn't correcting for the atmospheric conditions. So that was the second step. We did the atmospheric correction and we chose the dark subtraction so that we could convert that at sensor reflectance to at surface reflectance. So in other words, we were trying to approximate what the reflectance off the surface would look like as if there were no atmosphere interacting with the electromagnetic radiation between the surface and the sensor. But there are often other pre-processing steps that also need to be done before you can start with your classifications or biophysical modeling. And we're going to talk a little bit about each of these. Radiometric correction, it sounds a lot like a radiometric calibration, but remember, the calibration is when we were trying to take that radiation and convert it from raw digital numbers to reflectance. Radiometric corrections are when we are looking for errors within the image itself, and these are usually errors in pixel values. So in other words, the raw digital number that's recorded for a given pixel is incorrect, and there are a couple of different reasons why this can happen, but it's almost always associated with the sensor itself. So there are lots of individual detectors within each sensor, and those don't always function properly. Sometimes they turn on and off. Sometimes they will drift and are actually out of calibration. If you think about the push broom sensors that have multiple detectors lined up next to each other, all measuring the exact same wavelength or the same band, there is a chance that they're not all going to be exactly the same. So you may actually have one detector that is calibrated slightly differently, and so it will record a slightly different raw digital number than the detector next to it, and this could give you what looks like striping in your image. Sometimes there are just random bad pixels. The detector somehow turned off for that one location or didn't record for that one location, or there was an error in the file read, and you may have a pixel that just has a no data value, missing data. Now in the worst case, this can actually result in a shift of an entire line, for example if there were data missing. But in other cases it's literally just a zero value. It's showing up as a blank or missing data within your image. So we can fix these, and most software packages have automated tools that can do this, but essentially what we do is we assume that whatever is at this pixel is likely similar to what's surrounding it. And so what we do is we just take the mean value of all of these surrounding pixels and report that mean value in the center. And so you end up filling in for that pixel. You are essentially guessing at what the value is, but at least you don't have that zero value there anymore. And there are different types of filters too where you could actually weight these surrounding pixels differently, but the most common approach is just to weight them all equally and take a straight mean to report at that center value. So we refer to this as just random noise or shot noise. Another common radiometric error is a line drop, where essentially you have either a detector that completely goes offline and stops collecting data, so that as the sensor moves there's just no data for that location in the image, or as we saw with our Landsat 7 scan line correction error, you can have an issue with how the mirrors are sweeping from side to side across that scene and scanning across that scene. The movement of the the satellite is not being corrected or compensated for, and therefore we end up missing entire regions as that sensor is scanning back. So there are a couple different ways to correct this. One of them is very similar to that random noise or the shot noise. It's just taking the mean values above the line and the mean values below the missing line and just filling in with those average values. The problem with this approach, when we have really large lines, like with the scan line correction, it's really more than just one line that's missing. There's actually multiple lines that are missing. They get wider as you get towards the edges of the image, and that means that as we move farther and farther from our known actual recorded data values, that we end up guessing more and more as to what that mean is. So it is a little bit risky to fill in like that. Another approach that people will use is they'll find another date of the same location, the same sensor, and they will mosaic those two together so that essentially that second date will just backfill, and wherever there's missing data, the second date will fill in and will show up. Another common radiometric error in scanning sensors is what we call a bad line start. So these sensors have these mirrors that sweep across the scene back and forth. And as they're sweeping from one side and then back to start again on the other side, the detectors shut off, they stop recording, and they turn back on as they start that sweep again. And sometimes they don't start at exactly the same time, and so you end up with these images that have a whole bunch of detectors that start on cue, but then a couple that start a little late. And what it does is it essentially offsets that entire row of data. So there are scripts that we can use to identify which rows have these bad line starts, and we can essentially just push them over. So again, this is another tool that you might need to use to pre-process your imagery before it's really ready for your additional analysis. More common in the push broom sensors when we have an array of detectors and each detector is recording for a different location across the image. If these are not all calibrated to each other perfectly, you can have some that look slightly brighter or slightly darker than their neighbors, and this results in the striping your image, and you can see this throughout the entire image. We can identify these pretty easily with some automated scripts, and usually the first step to this is taking a geographic profile for each band. So for example, what this shows here is each pixel going from the western side of my scene all the way over to the eastern side of my scene. So it's looking at the mean value for each column of data. And you know you have a striping issue when you see these rugged peaks. In a natural heterogeneous environment, you would not expect to see this sequence of ups and downs like that. It should be much more random and smooth. But we can use this profile to identify which columns have these brighter values and which columns have these lower values, and we can see by how much those are offset and apply an adjustment to smooth them out. And this is much more what we would expect to see if we were looking at a spatial profile for one given band. And you would just repeat this for each band. The fix is not always perfect, but it's certainly a lot better than what you had to begin with. So that about sums up the various types of radiometric error and how we might be able to correct for them so that we can then go on and do some real analyses with our imagery. Until the next video, enjoy.